Leonardo is a researcher at Paris Tech, and he will talk about end-to-end similarity learning and hierarchical clustering. Please go ahead.
Can I see it? So, good morning, everybody. Thank you to be here. Welcome to my presentation titled End-to-End Similarity Learning and Hierarchical Clustering for Unfixed Size Dataset. This work is a joint work with Beatriz Marcotegui and Santiago Velasco-Forero in the Center of Mathematical Morphology in Paris Tech. So in this presentation, okay. No, okay. So in this presentation, we are going to do a short introduction on hierarchical clustering, and then we are going to see some literature, in particular one paper on embedding hierarchical trees on a hyperbolic space that is the Poincaré disk. And then we are moving on our contribution of our paper that we presented here, that is how to learn a similarity function for hierarchical clustering. And we show some experiment that we did on toy dataset, and we'll draw some conclusion and perspective. So hierarchical clustering, as you already may know, the idea is to try to, given a bunch of data, we want to extract a family of nested partition of the data in order to iteratively group elements together in multiple levels. To model the relationships between objects, we can use either a distance function or a similarity function. And if we have a distance function, we can define a similarity function. So in this presentation, I will use both of the two. And when you see W, I mean similarities. When you see D, I mean distance. So in classical literature, one approach to hierarchical clustering is for example, the one used with a single linkage criteria, when we start them from the bottom to define the hierarchies. Basically, what we do is to start from the finest possible partition, where we define each element as a cluster as a clusters, and then we start merge iteratively elements together to create a new partition. And the idea is that to use the linkage criteria to measure the distances between the clusters. And we do this iteratively until we reach the final partition, that is the trivial one, and the union of all this partition that we have found gives us the hierarchical clustering. And we also can compute at the same time the dendrogram. And if we cut the dendrogram at a given level, this gives us a flat clustering. So along with the single linkage criteria, there are other well-known criteria used in applications such as the complete linkage and the average linkage. The main difference is the way we define distances between clusters. So in the single linkage, we take the minimal possible distances between two elements in the different clusters, while in the complete, we take the maximum, and this will give us more compact clusters, while in the average, we take an average between elements, between the distances of different elements. Along with this approach, in 2016, Dasgupta came with a discrete optimization approach. His idea is to use a cost function to evaluate the quality of our hierarchies. And according to his cost function, a good hierarchy is the one that merge the most similar couple of points together at the beginning. Indeed, in this formula, as you can see, the similarity score between two nodes I and j is multiplied by the number of leaves contained in the subtree of the hierarchies rooted at the least common ancestor between the node I and j, the leaf node I and j. So if 2 points really similar are merged together at the beginning, this quantity here would be small. And for this reason, good hierarchies are the one that merge most similar points together at the beginning. The problem with this kind of approach is that finding an optimal solution that solves that the optimal solution for this cost function is indeed NPR. For this reason, other approaches that use a continuous relaxation of this cost function has been proposed. In particular, the one that embeds hierarchical trees. Sorry, there is something strange going on. Okay, sorry. Approaches I was saying that embeds hierarchies on the hyperbolic model, that is the Poincaré disk model, that can be obtained as a stereoscopic projection of the hyperboloid into the unitary disk. And this is particularly suitable because since it has a negative curvature, it makes this space particularly suitable to embed hierarchies. And geodesics in this space, as you may know already, are segments orthogonal to the boundary of the ball or straight line that pass through the origin. What Chami and colleagues proposed in 2020 is to try to, they proposed to do a continuous version, an hyperbolic version of the Dasgupta cost function on the Poincaré disk. And for this reason, they needed to define what is a least common ancestor on the Poincaré disk. And their definitions comes as the closest point to the origin on the geodesic path that connects to the 2 points. Their idea is that given n points on the Poincaré disk, we can decode a binary trees using a paradigm, a union find paradigm similar to the one that we have seen at the beginning. So basically, given 2 points, we start merging, we merge the most similar couple of points based on the hyperbolic HCA, and we iterate this process. Along with this, they also proposed a cost function to evaluate the quality of an embedding, and they also proved that the trees, binary tree that we can decode from this embedding, from the optimal embedding according to their cost function, is indeed an approximation of the optimal hierarchical trees according to the Dasgupta cost function. So far, this is really beautiful. The only problem is that we always work with a dataset of fixed size, and so when we want to add other points to the dataset, we need to recompute everything from scratch. So our idea, it was motivated to an application to 3D point clouds. In this case, what we want to do is to try to extract hierarchical decomposition from object described using 3D point clouds. And the problem here, as I said before, is that the sizes of different samples may vary, and what we want to try to achieve is, given different instances of the same object, we would try to extract similar decomposition, similar hierarchical decomposition. For this reason, since we think that the similarity function defined at the beginning affect the quality of the results that we can obtain, we wanted the proposed approach was to look for a good similarity function that, and the idea is to use a neural network to extract meaningful representation from the input set and then compute the similarity function as the cosine similarity of the hidden representation. We use the cosine similarity simply because it's conformal with the metric used that we have on the Poincaré disk. And we add a triplet loss margin term on the hyperbolic cost term used by Chami and colleague. And so our framework is a semi-supervised learning approach. We have the input points here and the label of points. We have labeled only for a subset of the entire dataset. And we use a neural network to project the input point on R2. And then we move to Poincaré disk using a normalization factor. And the neural network that we use is implemented in our test, we used either a multi-layer perceptron because we wanted a neural network that was invariant under permutation of under any permutation of the input set, or dynamic graph CNN that is a really famous architecture used on point cloud segmentation. In this talk, however, we will concentrate only on the results obtained using the multi-layer perceptron. As I said, this is a preliminary, we will show some preliminary tests that we did on a synthetic dataset. We can generate data sets that has different clusters. Here we show two examples. One are synthetic circles that in which we can change the number of points, and we use a noise factor to make the separation between the two clusters more difficult. Or we can generate the classical moons example. And here we have 4 moons instead of 2. And as I said before, we can play either with the number of points, either with the value of the noise. And since we wanted to evaluate the robustness of our network to the noise, what we did, it was to train the neural network on samples that doesn't contain noise, and then we test on noisy examples. So these are the samples that we used during training. And here we show some results that we obtained on the circle dataset. Basically, here we have the 5 figure. On the left, we have the input sample, then the either representation that we obtained using the neural network. After the 3rd figure contains the rescaled input representation on the Poincare disk. And finally, we have the dendrogram and the prediction. The prediction are obtained cutting the dendrogram in order to maximize the adjusted run index score. In this case, we have a perfect reconstruction. The color that you see for the first figure are the ground truth. The points are colored according to the ground truth. For the other one are colored according to the prediction. As we start increased noise, another things that I want to underline is that the embedding are indeed projected over, it seems, a straight line that passed through the origin, and the network separates the points of different clusters into very well in this case, and these are places on opposite direction opposite position according to the origin. And as we start to add noise, we can see that the arc of circles spread by the hidden representation on the Poincare disk becomes wider, and until the noise is too large. But even for high values of noise, we can still achieve a good separation until the noise is too large, and we start to have some issues. Similarly, for the moon's case, where instead the points are projected over the axis, the 4-axis, and then as we start adding the noise, we see similar phenomena as before. From as you can see here, from a qualitative point of view, we compared our method against the classical results, against the classical algorithm, and as you can see here, the red plot, the red curve is the one that uses is our method using the multi-layer perceptron algorithm, and is the one among the others that seems to be more robust to the noise. So as conclusion, we have seen a novel approach for hierarchical clustering for variable size samples, and the proposed framework that uses multi-layer perceptron has shown a higher robust to noise compared to classical algorithms. And as perspective, we would like to test this framework on real cases on 3D point cloud samples, and also use some other kind of architecture that are invariant to rigid transformation on the space that could be really interesting for practical examples, and also use add another network to embed the hidden features on the Poincaré disk. Thank you very much. If you have any questions.
Thank you. Thank you for a great talk. Maybe I can start off with a quick question. So when you compute you use the cosine similarity for computing the similarity between the embeddings. I was wondering, is this a constraint choice? You mentioned it had to be conformal.
Well, the problem is, from my point of view, it was since I was adding the triplet loss cost function to the hierarchy, to the cost function proposed by Chami and colleagues. Since I have to do derivatives, I wanted something that could use the same metric.
I see. So is it in that sense a convenience choice, or are you restricted to these type of?
Yeah, I'm some sort of restricted due to this fact. Otherwise, I should like separate the two loss function and optimize them differently on the two spaces.
Okay, that makes sense. Yeah. Are there any questions from the audience?
So just to be sure I understand, so in the function you minimize to train your network, there's two parts. So one is supervised and one is unsupervised. Is it correct? Or?
Well, it's a semi-supervised.
Yes.
And the things that I minimize is just I mean, I used only the labels on the.
So for instance, in the numerical example you show, there are some points that are actually labeled.
Yeah.
So what is the fraction of this point?
It's 30% of the entire sample.
And then in your loss function, there is also something that depends on the clustering method. So, and then you need to somehow backpropagate through this to learn the parameter.
Can you restate the?
In the energy you show, there is some part that depends on the hierarchical clustering, right?
Yeah.
And is it clear that you can backpropagate to this and things works nicely and there's no problem?
Yeah.
Okay.
Okay, thank you. I don't think there are more questions from online, and in the sake of time, maybe it's best to proceed.
Okay.
Thanks again for a great talk. So we continue the session. Gabriel Ferre chairs the